Today I want to talk to you briefly about section 2.2.1, which is the complex numbers and the complex plane. Of course, we can identify any complex number as x plus iy, where x and y are the real numbers. We also can identify that with a point xy in the coordinate plane r cross r. Once we do that, we call that new plane the complex plane, and what it does is provides us with a geometric way of representing all the complex numbers. So again, when a complex number is in the form x comma y, we call that the coordinate form, and x plus iy, we call that the rectangular form. Later on in the next section, and in this section, we'll look at some other forms of complex numbers, so it's important to understand the terminology. In the complex plane, we use the traditional, what is thought of as the Cartesian plane, except now the x-axis we use to graph the real part of a complex number, and the y-axis we use to graph the imaginary part. So, on this graph, those points represent 0, 1 is I, 0 being the real part of I, and 1 being the imaginary portion of I. I squared is represented by -1, 0. I cubed is represented by 0, -1, and 1 is represented by 1, 0. Geometrically, we can think of complex numbers as rotations in planes, and so it'll make sense why we can use the complex plane or the Cartesian coordinate to graph complex numbers. A rotation about 180 degrees about the origin will take the point 1, 0 to -1, 0. Or more generally, we can think about a rotation about the origin taking a point xy to the value x -y. You can see that here in this graph, where we start off with the point 2, 3, we're rotating about the origin, and it will simply take the value 2, 3 to the value -2, 3. So, another way we can think of a rotation of 180 degrees about the origin geometrically is it's simply multiplication by -1. Using that theory, we can easily see what we find when we talk about rotation of 90 degrees. A rotation of 90 degrees is equivalent to a rotation of 180. Two rotations of 90 degrees is equivalent to a rotation of 180 degrees. And of course, we know a rotation of 180 degrees is simply given by -1. So when we rotate 90 degrees about the origin, what we'll see is that that is equivalent to multiplication by square root of -1, or by I. So here we have the value 2, 3. Again, this represents the complex number 2 plus 3i. And when we rotate that value 90 degrees about the origin, it will become the value -3, 2, or -3 plus 2i. You can see that carried out here algebraically. We begin with the value 2, 3, and we want to rotate this value 90 degrees about the origin. That will be equivalent to multiplying the value 2, 3 by I. Once that is done, you can see by the computation that we do in fact get the value -3, 2, as we already have seen geometrically. A complex pair written in coordinate form, we can add and multiply complex numbers. As you'll see, the addition in the coordinate form is very nice, but the multiplication is quite cumbersome. Later on, you'll see that when we switch to polar form, the multiplication of two complex numbers becomes quite beautiful. Here's our definition. If A and B are rational numbers and C is a positive rational number, where the square root of C is not rational, then you should know that when you teach several algebra concepts, when you look at a plus b square root of c and a minus b root c, we call those irrational conjugates. The word conjugate comes from the Latin form conjugatus, and it means joined together. The reason that they use the word conjugate, meaning joined together, is because you should recall that we get irrational conjugates as solution to quadratic equations. So they always, of course, come in pairs. Now, from irrational conjugates, we can get something called complex conjugates. If given z equals x plus iy, the complex number z bar equals x minus iy is called the complex conjugate. You'll see why that comes into play as well. It'll of course have something to do with those quadratic equations that we always know. Let's talk about some more geometric interpretations of complex numbers. Hopefully you know that the absolute value of x represents the distance from x to 0 on a real number line. Well, for complex number z, the absolute value of z refers to the distance of z from the origin in the complex plane. So you can kind of think of that as, of course, the radius. The modulus of z is the absolute value, which is equal to the square root of x squared plus y squared. Of course, remember this z here is in the complex plane. One question that one may ask is, what is the set U of all complex numbers z such that the modulus of z equals 1? Again, the modulus of z equals 1 means you're looking for all points in the complex plane that have a distance of 1 from the origin. Well, what is that? Of course, it's the wonderful unit circle. Now that we have the idea of distance in the complex plane, let's look at how those complex conjugates relates to those quadratic equations. So on the next slide, what I'll do is graph these three equations in the real plane. So I'll graph y equals x squared plus 2x minus 3, y equals x squared plus 2x plus 1, and y equals x squared plus 2x plus 5. Then I'll graph the solutions to the quadratic equations below. Alright, the first thing at the top you'll see is this graph of the three equations. So notice that the first equation has two complex solutions. The second equation has a double root solution, only crossing the x-axis at x equals -1. And then the third equation has two specific real solutions, x equals 1 and x equals -3. Below, what I'm going to show you is a graph of the equations y equals x squared plus 2x plus 5 and so on. And on the right side you'll see a graph of the solutions, and I of course have to graph the solutions in the complex plane. So the two red points represent the solutions of x squared plus y equals x squared plus 2x plus 5 equals 0. Which of course has no real solution but does have two complex solutions. Again, notice that they come in pairs. These are two complex conjugates, -1 plus 2i and -1 minus 2i. Then you see the double root given here. And lastly, you see the last equation that has the two real solutions. Again, you can see that they're -3 and 1. What you'll see is that as the constant term increases from -3 to 1, solutions move inward towards x equals -1. As the constant term then increases from 1 going toward 5, the double root then splits into a pair of complex conjugates that are symmetric about -1. So they all the complex solutions will all be symmetric about -1. You can see this a little quickly. I won't go through all of it, but if you simply look at what the solutions of this equation would look like with any generic constant term c. Once you do that, you have x squared plus 2x plus c equals 0. You can of course solve that using a quadratic formula, and you'll get that x equals -1 plus or minus the square root of 1 minus c. Of course, the discriminant of this will tell us what types of solutions we have, and thus will give us whether or not we're going to have solutions that lie on the real part in the complex plane, or if they're going to be symmetric to -1. Lastly, I'll talk a little bit about polar forms, which will be crucial, especially when we talk about powers and multiplication of complex numbers. So polar form is given by, we use brackets r comma theta, and this is just another way to represent a complex number x plus iy. So here I've drawn a picture. Suppose you have a complex number x plus iy. So say this here is your complex number. Then the way we go from complex numbers to polar form is that r is going to be this distance from the origin to our complex number, and theta is going to be this angle here from the real part to whatever this actual line is. So again, we have a new form. We have the coordinate form, which we already knew. We have the rectangular form, and now we have the polar coordinates. And in polar coordinates, the r coordinate we call the modulus of z. Again, it represents the distance from the origin to the complex number. And theta we call the principal angle, or it's also known as the argument of z. One thing we often want to do is convert from rectangular to polar form. Again, when we do multiplication, you'll see why this is very beneficial. So to convert from rectangular to polar form, we simply use the fact that, of course, r, since it represents the distance from the origin to our point, we of course can use our fabulous Pythagorean theorem to know that r has to be equal to the square root of x squared plus y squared. Then using our trigonometric functions, we know that the sine of theta is simply y over r, and the cosine of theta is x over r, both of which will allow you to find out what the angle theta is. Theta does have one restriction. It has to be greater than negative pi and less than or equal to pi. Hence, our formula for y and r are y equals r sine of theta and x equals r cosine of theta. These equations allow you to go back and forth between rectangular and polar form. Lastly is an example of a complex number in rectangular form and the complex in polar coordinates. Again, you should be able to use the information on the previous slide to go back and forth between rectangular and polar coordinates. I won't show the derivation of that, but you definitely want to make sure that you know how to do that. That completes my summary for section 2.21. As always, be sure that you have read all sections. I simply highlight some of the important information.